All right, we're almost done. So at the very beginning, we probed our inputs, and then we measured, and then we performed operations, and we selected which operations we wanted to output. Now we have to take those outputted operations and format them in a way that can be read by the microcontroller. So the microcontroller can only read positive voltages and can't read very large positive voltages either. So in order to do that, we have to do a bit of signal conditioning to make this work. So the first thing that we are going to do here is you notice that there's this voltage divider right here, and this is to extract -5 volts. So with this extracted -5 volts here, it gets put into this buffer. Oh, this is named incorrectly, so there should be 5 volts here, and this should be 5 volts here. And this buffer doesn't change its value, just buffers it to make sure that it's -5 volts. So this -5 volts is then added with the input. So that might seem like subtracting 5 volts, but since this is an inverting summing amplifier, this will actually add, well, this will subtract -5 volts from this, but then it will also invert it, so that way it'll appear as 5 volts larger, or as +5 volts at the very end. So after it's added with the inverting adder, there's this diode right here. This diode is just to make sure that there are no negative values, because if there's a negative value, this diode will become a short and the signal will approach 0. So this is just to make sure that there are no negative values, because the microcontroller can't handle negative values. But that doesn't solve the problem, especially since we added 5 volts here. The signal here might be very large, probably too large for the microcontroller to handle. So from here, we have this 10-to-1 inverting amplifier. So what this does is it'll invert the signal again, and it will also divide it by 10 based on this voltage, based on this resistor ratio of 1 to 10. It'll divide it by 10, so that way it's 10 times smaller. That way it's a small signal that the microcontroller can read, and it's also been inverted. So notice how this summing inverting amplifier inverted it, and this scaling inverting amplifier inverted it again. But remember when I talked about earlier in the operations, all my operations were actually backwards because we would have to invert them at the very end. Well, here at the very end, we have another inverting amplifier. This one has a gain of 1, so it's just an inverting buffer because of these resistor ratios of 10K over 10K, which gives you 1. And so this will just do another inversion. This will allow us to recover the corrected signal at the output. So now here we have 3 different outputs, and I have 3 different outputs here because originally the system is able to communicate with itself, so that once you decide its voltage divider ratio, the system knows what voltage divider ratio you selected. Unfortunately, with this TINA model, each circuit is independent, so this circuit has no idea what voltage ratio we chose for the voltage selection way back in the earlier circuits. So in order to fix that, I have this manual selection circuit. And this circuit, and these switches are used to select which turns ratio, or which voltage divider ratio we used. So since we used the voltage ratio 1 to 10 at the very beginning, I'm going to set the output, this one, microcontroller 10 to 1 to 10, and I'm going to set these two to -V. This will produce a negative voltage, but this won't be inputted into the microcontroller. This is just to note that these channels aren't to use. So these will produce negative voltages right here. And so this is with the 10-to-1, because we used the 10-to-1. And so then we just have to input our input our signals. And remember, we had 3 signals. We have the channel 1 pass through, we have the channel 2 pass through, and then we have the actual operation. So first I'm going to do let's do the channel 1 output first. So if you remember, it looked like that. All right, I'm going to run the transient for 1 millisecond. So notice how it doesn't look like much, because there's this -12 volts from the other 2 channels. So in order to actually view it, I'll need to separate these curves. So see, it's very small now. Notice how it's only 500 volts to 700 volts. It needs to be small because the microcontroller can't read large voltages. And it's above 0 because the microcontroller can't read negative voltages. And these other inputs are just -12 because I just set them there to denote that these aren't being used. So from here, I just have to export this as a text file, same as always. So this is going to be channel 1 microcontroller. microcontroller. All right. Can do the same thing with channel 2 and the operation. So then we're going to do the same thing. Oh, oops. I'm going to open. And this is going to be channel 2 output. Okay. This then looks like that. All right. Run the transient again. Looks like that. Doesn't look like much because of that negative 12 down there, so I need to separate the curves to see it. Notice how with that extra invariant amplifier, it's back down to being negative, or at least, well, it's not negative, but dipping downward instead of peaking upward because it's been inverted again. Notice how even with this negative peak, or with this dip downward, it's still above 0 at 300 millivolts here. These are both negative 12 to denote that they aren't being used, so then I just need to export this one. So this one's going to be channel 2 microcontroller. All right. So the last one I need to output is going to be the operation. So open this one. This will be the operation output, which is here. So remember, it looked like this. It looked like the rectified waveform, but it was inverted. But after running through this, it should be non-inverted. So then I run through this again. And then I have to separate the curves to see the difference. See, now it's rectified. See, now it's going upwards and it's above 0. So then I can save this one or export it as a text file. This is going to be operation microcontroller. All right, now for each of these, I'll need to extract them in Excel now. So now we're going to do a bunch of Excel work. So let's start with channel 1. So I look at channel 1 microcontroller. Where I put it, which I put it here, here, channel 1 microcontroller. Open it up. Again, it's tab delimited. So go here, go over here. So now we're going to use a different macro. So if I look at my list of macros, I have this third macro, which is called CSV samples. Because since we're done operating on the data, we need to put it in a format that can be read by the microcontroller. So this macro's job is to format this data so that way it can be read by the microcontroller. So I'm going to run through this new macro, which is called CSV samples. I'm going to run through it, and it's going to output it like this. So the first row represents the time period of the measurement in milliseconds. So this is 1 millisecond because that's what the simulation time I set up throughout the system was, 1 millisecond. So that's why this is 1, because this represents the time in milliseconds. This represents the offset in millivolts. So if you notice from all of our signals, if I open it up, the offset, it was always offset from 0 by about 100 millivolts. So that's what this offset is. The microcontroller needs to know what this offset is so that way it can perform the correction to extract the correct signal from this signal. So that's what that offset is. And the last line is going to be the is going to be the voltage divider ratio. Originally, the voltage divider ratio was 10, but if you noticed in our circuit, we divided by another 10 right here. So that way, the total ratio that needs to be multiplied is 10 times 10, which is 100. So the signals need to be multiplied by 100. So that's what this 100 here is for. And then all these signals afterwards are all just the data points. So from here, we're going to save it, but we're not going to save it as tab delimited because our microcontroller doesn't read tab delimited files. It reads comma delimited files, or CSVs. So it's going to look like this. So this is what it's going to be. Channel 1 microcontroller is going to be a CSV now. So I save this. All right, and we're good to go. So now I have to do the same thing for the other two outputs that we had. So for the next output, we had channel 2 microcontroller, tab delimited. So another small thing to note, this still has 10 times as many samples, but since I'm not operating on this data anymore, I don't care or I don't need to reduce the number of samples to reduce, because the only reason why I reduced the number of output samples was to reduce the simulation time. But since I'm not doing any more simulations with this anymore, I can keep the extra samples to help make my curves look more smooth when I display them. So next I have to run CSV samples. So I run that again. And again, 1 millisecond, 500 millivolt offset, and you need to scale by 100. All right. Save this as not text tab delimited anymore. Now it's going to be CSV. So this is going to be CSV here. All right. All right, last one. We're going to open this up, and we're going to open up operation microcontroller. Operation microcontroller, there it is. All right, tab delimited, right, looks good. Now we have to format it correctly by using the CSV samples macro. So that's formatted 1 millisecond, 500 millivolt offset, scaled by 100. All right. Again, we're going to save this as CSV. All right, and now we're good. So those 3 CSV files that we just made will then need to be imported into the microcontroller. And then from there, the microcontroller will read those CSV files and display the signals that we observed through the simulation onto the digital display. And it can measure various properties of the displayed signals, just like an oscilloscope, like maybe measuring peak voltage or frequency or things like that. But in terms of the analog section is done. From here on out, the microcontroller will take care of this reading and displaying the data after we formatted it.